Data Management. I'm Saurabh Bhomik from NTU Singapore, and I'll be chairing this session. We have 8 papers for this session, 4 for 20 minutes papers, and the remaining 4 are on 10 minutes. So without much further ado, I would like to invite Choo Tian to present the first paper on numeric inconsistency for graphs.
Good afternoon. I'm going to talk about catching numeric inconsistencies within graphs. Recently, a variety of dependencies have been studied for graphs. For instance, we all know that if a person has 2 birthplaces, then they must be the same. This rule can be expressed as a graph functional dependency that defined in terms of a topological structure. In addition, the relational keys are also extended to graphs to identify vertices that refer to the same real-world entity, like the albums can be identified by their names and recording artists. There are also some constraints proposed for RDF data in similar ways, which aim to capture inconsistencies among entities. In general, all these dependencies specify the semantics in schemaless graphs and are useful in knowledge-based enrichment, fraud detection, and conventional query optimization. But what happens when the graphs carry numeric values? We find numeric values are often involved in the semantic errors of real-life graphs. For example, DBpedia records the population of 2 cities in California at 2014, where Corona has 116,000 people and ranks 33rd by population, while the other city, Donny, has a smaller population and ranks 11th. That's a conflict. It also says John Macpherson was born in 1713 and is still alive, which exceeds the human lifespan. For the third one, we discover from DBpedia that 24 athletes from 34 countries competed in a game at the 1992 Summer Olympics. It contrasts to the common sense that each player can represent at most one nation in Olympics. To catch such inconsistencies, we have to use comparison predicates like greater than to compare different values. That's beyond the equality that's supported by existing graph dependencies. Here are some other cases taken from Yago and DBpedia. It is recorded in Yago that an institute BBC Trust was created after the time it was destroyed, which must be impossible. And in Yago, we also found a village in India has about 1,500 people, but that's different from the sum of its males and females. The next one concerns the Formula 1 racing. In DBpedia, Sebastian Vettel and Max Verstappen won 1 race in total in the season of 2016. However, they're representing a constructor team. Ferrari didn't win any in the same year. We can see that the arithmetic operations on numeric values are necessary in detecting the errors on this page. So the examples raises several questions. Firstly, how should we extend graph dependencies to catch numeric inconsistencies? And does the extension make it harder to reason about the dependencies? Moreover, can we develop a uniform framework to detect errors in real-life graphs, whether numeric or not? And this work tackles the questions. We first extend graph functional dependencies by incorporating both arithmetic expressions and comparison predicates, namely a new class of numeric graph dependencies, and we call them NGDs. Each NGD consists of a graph pattern Q and an attribute dependency in the form of X implies Y. The pattern is indeed a topological constraint to identify the entities within a graph, which also indicates the scope of the attribute dependency to be enforced. And X and Y are sets of literals defined with arithmetic expressions connected by several built-in predicates, not limited to equality. The expressions E support common arithmetic operators, including the absolute value. And its basic term is either an attribute from the pattern or a constant. Moreover, the degree of E is at most 1, so we only consider linear expressions. For the semantics, we say a graph G satisfies NGD if for all the graph homomorphic mappings from the pattern Q to G satisfy the literals in precondition X, they also satisfy the literals of Y. And standard semantics of arithmetic operations and comparisons are used to decide whether a mapping satisfies a literal after instantiation. Having defined the NGDs, let's look at some real-life examples. Suppose we want to state that if a city X has more people than another city Y in the same population census, then X should rank ahead of Y in terms of population. Then simple NGD suffices. It uses a tree structure pattern to identify the cities and the census. And two built-in predicates greater than and less than appear in the attribute dependency to compare different populations and the ranks. This NGD can detect the error we have seen earlier in DBpedia, in which Corona and Donia mapped to pattern nodes X and Y, and the attribute constraint is applied there. Next, consider this rule that each player represents at most one nation in Olympic Games. We can write it as an NGD with the help of a comparison predicate. And this one also means the number of participating nations in an Olympic event is less than or equal to the number of athletes. So it catches the inconsistency related to a computation at 1992 Olympics, which we encountered in DBpedia. And if we further require each nation just select a single athlete, then equality checking among the two values is enough, and graph functional dependency works under this case. So the existing graph functional dependencies are just a special case of NGDs. As another example, we know in Formula One racing, the total number of competitions won by two drivers should not be larger than that of their team in the same season. The corresponding NGD includes a cyclic pattern, and both arithmetic operators and the built-in predicates are incorporated in the attribute dependency. It captures the error in DBpedia among Vettel, Verstappen, and Team Ferrari. Here, all the number of races, all the number of wins are correct, but Verstappen didn't race for Ferrari in the season of 2016. So the NGDs help to detect erroneous links in real-life graphs. Apart from catching inconsistencies, NGDs also facilitate spam detection in social networks. To decide whether an account Y is fake or not, we really need to check the gap between the number of followers and the followings of a real account X and account Y. So consequently, arithmetic calculations and comparisons must be conducted. For this reason, we embed the condition into an attribute dependency of an NGD and make use of an additional pattern to locate the candidate fake accounts first. So in the second part of this work, we investigate two classical problems for reasoning about NGDs. The satisfiability problem is to decide whether a given set sigma of NGDs has a model, namely a graph G that satisfying the NGDs in sigma. And the implication problem concerns whether a set sigma of NGDs entails another one, phi. In other words, for all graphs G that satisfy sigma, whether G also satisfy phi. These are not only of theoretical interest, but also find practical applications. The satisfiability analysis enables us to check whether a set of NGDs is dirty before being used as data quality rules. And implication analysis helps to remove redundant rules so they can optimize the data cleaning process. We find the satisfiability and implication problems are sigma 2p and pi 2p complete respectively. And the lower bounds still hold when either arithmetic operations or comparison predicates are present, not necessarily the both. So the robust complexities do not come from the interaction between the two, as opposed to the counterparts, to the NP complete and the co-NP complete for the counterparts of graph functional dependencies. The increased expressivity of NGDs pays a price. We might also want to extend NGDs by allowing nonlinear arithmetic expressions. That is, the maximum exponent in the expressions is not restricted to be 1. Unfortunately, this extension makes the static analysis undecidable, even for NGDs extended with expressions of degree bounded by 2. So this result justifies our choice of linear expressions for NGDs, which strike a balance between expressivity and complexity when arithmetic and comparisons are must. Now I'd like to move to the third part. To make practical use of NGDs, we develop techniques for detecting errors in real-life graphs by employing NGDs as data quality rules. It is to find all the violations of a given set NGDs in a graph, and each violation includes inconsistent entities that violate the attribute constraint. It is known the decision problem for error detection with graph functional dependency is co-NP complete, and we find the problem gets no harder for NGDs. And better still, the parallel methods developed for graph functional dependencies can be readily extended to NGDs. Actually, the only change involves local checking of NGDs at each fragment of the distributed graph, and the generation of homomorphic mappings remain unchanged, which dominate the cost of the algorithms. The algorithms are parallel scalable that guarantee to reduce the running time with more processors. are used, so they can scale with large graphs by adding resources. As a result, we can uniformly detect errors in graphs with NGDs, whether numeric or not. As error detection is anyway costly and real-life graphs are frequently updated, we study incremental error detection as well. Specifically, we use a batch algorithm to compute the violations of NGD's sigma in graphs G only once, and then incrementally maintain them by computing the changes to the violations in response to the updates applied to G. This should be more efficient than recomputing the violations starting from scratch when the changes to G is small, as often found in practice. So practical methods with certain performance guarantees are developed for incremental error detection. On the one hand, by following update-driven evaluation, they are localizable, which assures the costs are determined by the size of D neighbors of the nodes involved in the input update. Intuitively, they reduce the computations on big graphs G to a smaller area that surround the input update. On the other hand, they are still parallel scalable, which is achieved by splitting skewed computations and by dynamically balancing the workload. These two features make incremental error detection feasible in large-scale graphs. We finally evaluated the methods on 3 real-life graphs, including both knowledge bases and social networks, and synthetic graphs. We discovered diverse and meaningful NGDs from the graphs, and in the incremental setting, the updates were randomly generated. We found incremental error detection is effective. The incremental algorithms outperform their batch counterparts when the input update accounts for nearly 30% of the entire graph. And the incremental detection algorithms take longer time when the diameter D gets larger. This is consistent with our analysis on the cost of incremental detection algorithms. For the scalability of the methods, we found the parallel algorithm scales well with the number of processors. The runtime is improved by almost 4 times when the number of processors increased from 4 to 20. And this also verifies the effectiveness of the dynamic load balancing strategy. To sum up, we have proposed a class of NGDs with arithmetic expressions and comparison predicates to capture numeric errors. The linear expressions in NGDs strike a balance between expressive power and complexity. We have also developed batch and incremental error detection approaches with provable performance guarantees. All these yield promising to detect errors in real-life graphs, whether as a numeric or not. Okay, that's all. Thank you for your attention.
Time for a couple of questions. Could you please connect to the mic?
Hi, thanks for the talk. It was really interesting. I was just wondering, when it comes to the NGDs, do you have to have some specific domain knowledge to describe them or to decide upon which ones you want to actually put into your system? Or can perhaps you sort of infer them from the rules and types within your own ontology?
Actually, we assume the open world assumption.
Okay.
Yeah. So in the experiments, we discovered the NGDs from real-life graphs, and by using algorithm, by extending algorithm on the discovery of graph dependencies, and it interleaves the two process for mining the patterns and the correlation of attributes at the same time. But the conventional support for patterns do not work for the NGDs. So we propose a new measure to a new criteria to measure the interestedness of NGDs and select appropriate attributes from the graphs, the attributes in the real life graphs.
Lovely, thanks.
Mm-hmm.
So just a quick question. So all of these constraints looks like you could probably represent them just as a bunch of joins. If I thought of the graph as edges table, and I thought of a pattern as a complex join, a constraint on the variables that essentially are assigned to the output tuples. Is there any benefit of thinking of all of this sort of theoretically in terms of graphs as opposed to joins?
So if we store the data in the relation, then yes, it's the same to the truant operation. But in graphs, actually, the algorithms are very different. For example, for detecting errors, we make use of the locality of graph mapping. So the cost of our algorithms is determined by just a small neighbor of the updates for incremental error detection. But in relational data, we have to use a bunch of joins to compute the matches.
So that's just saying like the join, a constraint on the output of a join would express exactly these graph pattern NGDs, right? So there could be differences in the evaluation of the join.
Yeah.
If you stored it as a graph, you could implicitly evaluate the join differently. Mm-hmm. But in terms of expressibility or what you can express as a constraint, it's they are equal.
Essentially they are the same.
Okay.
Right.
Just to follow up to the previous questions, I don't think it is useful to think that all the constraints of the graph can be done by joins. So one major thing over is the unbounded joins. So you go n times through the graph, but you don't know what that n is as part of your constraint. Another part is cycles, that you have to do the cycle detection. And not the graph can have cycles in there, but not always, so you have to detect those. And also aggregation is very important, like in the bill of material graphs, the weight of a product is more than the weight of its children, the subcomponents, plus of course its own at the higher level thing. Graphs. So there are a whole bunch of such things. And then the graphs, the other problem over here is that there is in the real applications, there is an overlap between constraints and fraud. Okay, so therefore we use machine learning, deep learning to figure out the frauds, and fraud in a way they're like constraints that they should not happen. So once you go over there, you see the complexity over there, and that's not just a bunch of joins.
Okay, all right.
Maybe we can take it offline from here. Yeah. Okay. Let's